Cardiovascular physiology, the integrative functions of the cardiovascular system. Welcome to our in-depth discussion on cardiovascular physiology, where today we explore the integrative functions of the cardiovascular system. This topic acts as a grand finale, tying together all previous concepts and highlighting the system's ultimate purpose, to dynamically and cohesively serve the needs of the entire body. Let's begin with the central concept. The cardiovascular system operates not as scattered, independent parts, but as a single, pressurized, and closed-loop circuit. Its primary mission is to maintain adequate blood flow to all tissues, giving priority to the most vital organs, regardless of the challenges the body faces. The system's integrative role is the constant, real-time coordination of the heart, blood vessels, and blood itself to meet the body's ever-changing metabolic demands while keeping the entire system stable. The four pillars of integration. To truly understand how this system works, we must look at four key domains where integration happens. 1. Integration of the components of blood pressure. At the heart of blood pressure regulation lies the relationship. Mean arterial pressure equals cardiac output multiplied by total peripheral resistance. Adjusting one factor inevitably affects the others, demanding continuous integration. In the short term, neural control systems like the baroreceptor reflex spring into action. Picture yourself suddenly standing up. If your mean arterial pressure drops, the body's response is immediate. The heart rate and contractility rises, the sympathetic nervous system increases its output, and the parasympathetic system decreases. At the same time, blood vessels throughout the body, especially those supplying the gut, kidneys, and skin, constrict to boost resistance. Together, these changes restore blood pressure. When it comes to long-term regulation, the kidneys and hormones take the lead. Imagine the body is facing a prolonged decrease in blood volume. The renin-angiotensin-aldosterone system steps in. Blood vessels constrict through the action of angiotensin II, while hormones like aldosterone and antidiuretic hormone promote the retention of salt and water. This increase in blood volume leads to a greater return of blood to the heart and ultimately a rise in stroke volume. As a result, blood pressure is restored by both increased resistance and greater cardiac output. 2. Integration of regional circulations. The shunt mechanism. The total volume of blood the heart can pump is finite, so the body must prioritize and redistribute blood flow based on immediate needs. Think of the cardiovascular system as a sophisticated irrigation network that channels blood to where it is most needed at any given moment. Local metabolic factors, such as adenosine, carbon dioxide, and hydrogen ions, dilate arterioles in active tissues. However, the sympathetic nervous system can override this local control, constricting arterioles in less crucial areas to maintain overall pressure. During dynamic exercise, for example, working muscles release metabolites that cause powerful vasodilation. Normally, this would drop overall resistance and blood pressure, but the brain and muscle reflexes trigger a massive sympathetic output. The heart rate and contractility soar, raising cardiac output by 4 to 5 times. Blood vessels dilate in the heart and working muscles, while those in the kidneys, gut, and inactive muscles constrict. Initially, skin blood flow is reduced, but as body temperature rises, blood is redirected to the skin to help with cooling. In the end, blood pressure is maintained or even slightly increased, and the blood is directed away from organs like the gut and kidneys to fuel the muscles at work. 3. Integration of the cardiac and vascular functions. The venous return and cardiac output loop. This aspect reveals the closed-loop nature of the cardiovascular system. According to Guyton's model, cardiac output and venous return are inextricably linked, two sides of the same coin. Their balance defines how the system operates. Venous return is influenced by the mean systemic filling pressure, which depends on both blood volume and the tone of the veins, as well as the pressure in the right atrium. Cardiac output, meanwhile, is shaped by heart muscle contractility, heart rate, afterload, and preload, the latter of which is determined by venous return. Take the example of hemorrhage, where blood loss reduces the filling pressure and, therefore, venous return. The body's initial response is to activate the baroreceptor reflex, increasing sympathetic tone. This elevates heart rate, contractility, and venous tone. Over time, hormonal systems like the renin-angiotensin-aldosterone system help restore blood volume, raising the mean systemic filling pressure and further improving venous return. The interplay of neural, hormonal, and vascular adjustments brings the system's equilibrium back toward normal. 4. Integration with other organ systems. The cardiovascular system supports every other organ system, and its function is deeply intertwined with theirs. Respiratory system. The right side of the heart pumps blood to the lungs for gas exchange. The act of breathing assists in returning blood to the heart, and the lungs adjust blood flow to match the distribution of oxygen and carbon dioxide. Renal system. The kidneys regulate blood volume and composition, playing a central role in long-term blood pressure control. They receive about 1/5 of the cardiac output to perform their filtration duties, which, in turn, influences the cardiovascular system. Nervous system. Rapid adjustments are orchestrated by the medulla and hypothalamus, which send autonomic signals to the heart and blood vessels, managing everything from blood pressure to body temperature and stress response. Endocrine system. Hormones such as epinephrine, aldosterone, antidiuretic hormone, and atrial natriuretic peptide provide long-lasting, system-wide regulation of heart rate, contractility, and vascular tone. Skeletal muscle system. Muscular activity is critical for returning blood to the heart during exercise, and working muscles are the main consumers of cardiac output during physical activity. The hierarchy of control in any given situation. The cardiovascular response follows a hierarchy. Local metabolic control ensures that blood flow matches the metabolic needs of each tissue, whether it is the brain during intense thought or muscles during exercise. Neural control steps in to maintain systemic arterial pressure, especially when local demands conflict with the need to ensure blood flow to the brain and heart. Hormonal control supports neural regulation and handles long-term adjustments such as blood volume changes. Conclusion. The power of physiological integration. The integrative function of the cardiovascular system perfectly exemplifies the idea that the whole is greater than the sum of its parts. The heart acts as the pump, the blood vessels are the pipes, blood is the transport medium, and nerves and hormones are the control mechanisms. Only through seamless cooperation can the system prioritize blood flow to the brain in emergencies, redirect it during heat or exercise, and maintain the internal environment that all cells depend upon. This remarkable integration allows us to move from rest to activity, adapt to changing temperatures, and adjust to postural changes, all while safeguarding the life-sustaining blood supply to our most vital organs. Thanks for tuning in. If you enjoy our content, please like, share and hit the subscribe button. It's the Everything Surgery Podcast. Dissect the extraordinary.